Our next and the last postulate is about measurement. So far we have seen that states are the vectors in the Hilbert space, the observables are the Hermitian operators, the dynamics are given by a Schrodinger equation, which is kind of related to the wave equation. So far, whatever we have studied, whatever the property we have seen or we will see, for example, the superposition of states, the entanglement which comes with the superposition of states, and some such properties, they can be seen in the classical optics. Classical waves also have superposition property. If we have a couple of more than 1 degree of freedom for a wave, we can probably see the entanglement properties also. What makes quantum mechanics really special is the measurement postulate. So measurement postulate is the most striking thing, which gives us all the advantages and all the mysteries in the quantum mechanics. We see the quantum key distribution gives us really absolute security in the communication because of the measurement postulate. We have quantum advantage because of entanglement, but measurement also plays a very significant role here. Let us say we have a quantum system in the state psi, and we are performing the measurement of an observable A given by the eigenvalue an and eigenvectors small a, cat an. So we have a setup, measurement setup. Measurement setups do not look like this, how I'm drawing, but this is just a conceptual representation. In this setup, the state psi goes in. It means the quantum particle in the state psi goes in. So we may or may not know what is the state, that is irrelevant, but the experimental setup is designed to perform the measurement of the observable A. Then the outcomes will be A1, A2, A3, and so on, all the eigenvalues. Whatever observable we have in quantum mechanics, when we perform measurement, then eigenvalues will be what we will observe in the lab. And they will occur with some probability, P1, P2, P3, P4, in the sense that if we send one quantum particle, it can click on any of these outcomes. It can fall on any of these outcomes. And if we repeat this whole thing n number of times, where n is sufficiently large, then it will click in the first one with n1 number of times it will click in the first one, n2 number of times it will click in the second one, and so on. And the probability P1 will be close to n1 over n, n2 over n, and so on. So let me repeat. We have an experimental setup which is designed to perform measurement on the observable A. Then we send the quantum systems identically prepared in the state psi, n number of quantum systems, and we send them one by one through this setup, and they will give us clicks over these outcomes. And after the probability of these clicks is given by the n1 over n. So the n1, so the particle reached the outcome A1 n1 number of times. The probability P1 is n1 over n. But how is this probability P related to psi and A? So the probability of outcome an is given by the measurement of the eigenstate of the observable A as an and psi mod square. So the probability of the outcome is given by an and psi mod square. This is called the Born-Rule probability. This is the first axiom this is the first sub-axiom of the measurement postulate. That the probability in an experiment, the probability of the outcome an is given by the corresponding eigenvectors and psi in a product mod square. Now we can see that sum over n p of an is sum over n an psi mod square. We can write it as sum over n psi an psi, and this is sum over n psi an psi, And since an are the eigenvectors of the normalized eigenvectors of the Hermitian operator A, they add up to identity. So if we take the summation inside, we get psi sum over n an psi, and this is 1. So if we add all the probabilities for all the outcomes, we get 1. This is and this is what any probability distribution should satisfy. Next is the expectation value, the average value of the observable A. And average value of an observable in classical statistical mechanics can be written as sum over n, an, the outcome, times the probability of the outcome, Pn. So this is in the statistical mechanics, this is the probability of an observable, where an is the value of the observable and Pn is the probability of that outcome. Now, if we use the Born probability rule for P of an, then we get sum over n, an, psi an modes. Psi an and an psi mod are same things. And this we can write as sum over n, an, psi an psi. We can take summation and an inside the we can rewrite it like sum over n, an outer product psi, and this is the spectral decomposition of the observable A, and we can replace it with A, so we get psi A psi as the expectation value. So what we have done is we have taken the classical definition of the average of a measurable quantity, and that is the value of the quantity times the probability of that outcome. And for the probability, we have substituted the Born rule of probability for quantum systems, and we got an expression for the average or expectation value of the observable in terms of the state of the system psi and the operator A. So this is the expression for the expectation value, and with this derivation you can see that the definition of this expectation value is inspired from the classical statistical average of any quantity. Of course, we can generalize this definition to find the expectation value of A square. So to calculate this thing, first we see that A square is nothing but sum over n, an square, an outer product an. This can be seen by taking the square and realizing that an and an prime are orthogonal vectors. So the average, the expectation value of A square will be psi A square psi, and that will be sum over n, an square P of an. And from here we can calculate something called the variance of A square, that will be A square minus A square, or that is A minus expectation value of A square expectation value, and that will be sum over n, an square P of an minus sum over n, an P of an. So we'll leave it at this thing, and we will use this expression for the variance. Or the second part of the measurement postulate is the collapse, wave function collapse. So we have the experimental setup A, we have state psi going in, particle quantum systems in the state psi identically prepared. One by one we are sending them in the setup, and we have clicks in some certain outcomes A1, AN. So with probabilities Pn given by the Born group. What happens to the quantum system after the measurement? So the fourth postulate, the measurement postulate, or the collapse postulate of the measurement postulate, states that the state of the system after the measurement collapses to the eigenvector of the observable corresponding to the outcome. That is, if psi goes in and we get an outcome, then the state of the system after the measurement will be an. So in this way, the process of performing measurement on the quantum system destroys or erases the information of the original state and replace it with the new state, that is the eigenstate of the observable A. So in that way, once we get a click in certain outcome, or once we get an outcome, the quantum system has lost all the information about its original state. So this state cannot be used to further perform measurement on it in order to get more information out of it, because there is no information left in it other than that it's in the an eigenstate of the observable A. In that way, when we want to perform measurement on a quantum system, we consider a large ensemble of quantum systems. Each of them, or every one of them, is prepared in the same state psi, and we send those states psi one by one through this experimental setup, and we collect the statistics of the outcomes. And from that statistics, we can calculate the expectation value of the observable, and that can be used for whatever processing we want to do. But we cannot use the same, we cannot infer any information from a single quantum system, because once we send single quantum system in the experimental setup, it collapses to one of the eigenstate of the observable, and it has lost all the information about it, and we cannot use it for extracting any more information. So in that way, we cannot get any information out of a single quantum system, because it will just give us one click. It will not give us any probability. It will not give us any information about the state psi. Hence, it is not possible to do any meaningful thing with a single quantum system. So this was the detailed explanation or discussion about the four postulates of quantum mechanics. We will, in this course, we will be coming back to these postulates again and again, and we will be going more and more details and find good applications or interesting applications of these postulates. Our next topic is Heisenberg Uncertainty Principle, and this shows a striking difference between classical and quantum world. So in classical picture, whenever we perform a measurement on a system A, and we get certain uncertainty, certain randomness in that system, this randomness does not affect the randomness of any other system under consideration. But that is not true in quantum mechanics. The full meaning of the statement will be clear soon, but we'll start here with the following. Let us say we have two observables, A and B. They are Hermitian observables. They are observable, so they must be Hermitian. So A has its own spectrum an and eigenvectors an. B has its own spectrum and eigenvectors. So the uncertainty in A, that is delta A square, which will be psi. So we have a quantum system with these two observable. We have a quantum system with these two observable, and the state of the system is psi. So the uncertainty in A is delta A square. That can be written as psi A square psi minus psi A psi square, or it can be written as psi A minus expectation value of A psi A square psi. That is the expression for the uncertainty in A. Similarly, we have uncertainty in B, delta B square, and that can also be written as psi B minus expectation value of B square. Now the Heisenberg uncertainty principle states that delta A square times delta B square will always be greater than or equal to 1 over 4 times mod A commutator B, expectation value of that. So what does it say is, if we have two observables A and B which do not commute, if we have such observable which do not commute, then the uncertainty in A times uncertainty in B is lower bounded by the 1 by 4 times the uncertainty in the commutator of AB. So this is a very strong statement, and it comes only because of the quantum mechanics, because in classical world we do not have observables which do not commute. Every observable commute in classical world. So in that way, the commutation is always zero. So there is no lower bound on the uncertainties of the two observables. Just to give you an example, we have x, the position operator, and the p, the momentum operator. From our quantum mechanics, we know the commutator of x and p is I h bar. So then our delta x square times delta p square will be greater than or equal to h bar square over 4. This is what it means. So it means in a quantum system, the uncertainty in x and p cannot be, product of those two cannot be less than h bar square over 4. Or in other way, if we perform measurement in x, then we get very precise value without any uncertainty tending to 0. That would mean that there will be infinite uncertainty in the momentum. So the proof of this theorem goes as follows. Let us go back to delta A square, that is psi A minus expectation value of A square. From here, let us define psi A, some vector which is not normalized, as A minus A acting on psi. We know it's not normalized, but it's some vector, and we will keep it like this. From here, we can write delta A square as psi A. Similarly, we can write delta B square as psi B. Psi B. It means that delta A square times delta B square is psi A, psi A, psi B, psi B. Now I would like to recall an inequality, and that's called Schwarz inequality. Which says that if we have vectors psi and phi, their norm, product of their norm, will always be greater than or equal to psi phi mod square. Let me repeat, if you have two vectors psi and phi, then the product of their norm will always be greater than or equal to the mod square of their inner product. Okay, that we have proven in our mathematical supplementary lectures. So we use this Schwarz inequality in the previous equation, and we get delta A square times delta B square, which is psi A, psi B, psi B. This will be greater than or equal to psi A, psi B mod square. So this is one statement. Now consider psi A, psi B. That will be psi A minus delta A and B minus delta B. Not delta A, sorry. Let me put A bar for the expectation value and B minus B bar, so that it's easier to write. Now we have two operators, A minus A bar and B minus B bar. So let us call them X and Y. So we are given X, Y product, which we can write as X commutator Y plus X anti-commutator Y over 2. that we can check. XY commutator is XY minus YX plus anti-commutator is XY plus YX over 2 will be XY. So it means A minus A bar times B minus B bar can be written as half times commutator of A minus A bar with B minus B bar. A bar and B bar are numbers, so we are left with only AB plus entity commutator of A minus A bar and B minus B bar. This implies that our psi A, psi B will be half expectation value of commutator of AB plus expectation value of anti-commutator of AB. Now, psi A and psi B is a complex number. A is Hermitian, so is B. It means commutator of AB, which is AB minus BA, is commutator of AB dagger minus. You can check that the commutator, if we take the dagger of the commutator is the operator. Of course, AB minus BA is some matrix, if A and B are some matrices. And if A and B are both Hermitian, then the commutator is anti-Hermitian. Anti-Hermitian is nothing but I times Hermitian. But the important thing is the expectation value of the anti-commutator is always imaginary. And the expectation value of a anti-commutator is always real. So we can write psi A, psi B as half times some real part plus I times imaginary part. So we can say psi A, psi B mod square will always be greater than or equal to the imaginary part mod square. That is 1 over 4, the expectation value of A, B commutator mod square. And from our earlier equation, we know that the product of the uncertainty delta A square times delta B square is greater than psi A psi B mod square, which is greater than 1 over 2 A B mod square. And this is the proof of the Heisenberg Uncertainty Principle, which shows that if you have two observables which do not commute, then the product of their uncertainty is lower bounded by their commutator, the expectation value of their commutator. This is a technical statement. What it means is if you cannot measure two non-commuting observables simultaneously with perfection. So that is what it says, that if you have two non-commuting observable, you cannot measure them simultaneously with arbitrary accuracy. One interesting thing which I like to point out here, in deriving the whole Heisenberg Uncertainty Principle, we have never used the collapse postulate of the quantum mechanics. We have only used the expectation value, we have used the commutation relation. So expectation values can be derived without invoking the collapse postulate. We just need the Bond rule of probability.